All right, now we're working on day 11. So today we're going to go over homework 3, and we're going to go back over interface instability. So I spent a whole lecture going over interface instabilities, but everybody was out because of the GR midterm. So I'm going to go over those again, kind of in a hurry. I'm also going to introduce new stuff there. I'm going to go over the derivation kind of quick, but then I'm going to go over the results of the derivation because that's really the I don't know what I care about. I care about the derivation. If everybody could do that derivation cold, I would be so stoked, but it's long, so I'm not actually going to ask you to do it. Okay, so there's going to be another homework up. Probably, if I can get my business together, it'll go up today. If not, it'll go up end of the day tomorrow. I can't get it done before the end of the day tomorrow if I don't get it done today because I got crap in the morning. And if I can't get it done and up the end of the day tomorrow, then it'll slip a week. But so homework will go up. The next homework will go up. You'll see it probably tomorrow. And then next week we'll go over that homework. So we'll do new stuff, genes instability and Rayleigh-Bernard convection on Thursday. Then next Tuesday we'll postmortem the next homework, and then we'll have a midterm review, and then 2 weeks from today we'll have the midterm. That'll cover chapters 4 through 7, basically everything we've done, plus the next homework. So today we're going to go over the homework that was due before the hurricane. I hope everybody had an excellent hurricane. I hope nobody's families are too hosed by the hurricane. This is definitely the nicest way to spend a week, randomly in the middle of the semester. I'm supposed to fill up those days and deliver 3 more hours worth of content to you in some way, shape, or form. I'm not sure the best way to do that. So we'll note that I said I'm going to think about it. That's as far as I get right now. Okay, so let's go over the homework. So the problem 1, derive the momentum equation from Euler and continuity. So momentum says, well, let's start with Euler and continuity. Euler is, the continuity, d by dt of rho plus div rho v equals 0. And Euler is d by dt vi plus vj dj vi equals minus 1 over rho, keep our notations consistent, di pressure. And what I want you to get is d by dt of rho vi plus div this tensor tij equals this p delta ij plus rho vi vj equals 0. So I want you to take these 2 things and put it into here. The one thing that a bunch of you did, fascinating. Sorry. Usually my wife doesn't text me in the middle of class, so I usually try to check, and that was not anything that was. Apparently I put the cream cheese in the cabinet instead of the fridge. Because you did. Pre-coffee brain is just a drag. There's this coffee paradox. You need to have coffee before you can make coffee. If you're not smart enough in the morning to make coffee, you can't get coffee. You're totally hosed. So, okay, this business, where are we at? So one of the things that a bunch of you did that I'm going to yell at everybody for is you had something like this, and then you had something like this. You cannot do that. So you got to be really careful when you can pull things into a derivative. It's got to be a constant. It's the only time you get to pull things into a derivative. So I'm not pointing fingers or judging any, the reason I give homework problems is so that people get it wrong, and then we can say, hey, that's not how you do it it this way. So, but this is one mistake that several people did, was just multiplying this equation by rho And then since you know what the answer is, there's some interesting stunts that get you there. So let me show you how this works. So you start with what you're looking for. Or start with the thing. So I'm going to start here and show that it's equal to this part. Does that make sense? So we start with d by dt of rho vi. And that's equal to, you have to product rule the whole thing out. You get rho d by dt of vi plus vi d by dt of rho equals stuff. We'll figure that out. So now I'm going to take these two things and I'm going to stick them in. And so into this I get rho times, we got to huck that guy over to the other side, and we got to huck this guy over to the other side so that we can plug these things in. So this gives us minus vj dj vi minus 1 over rho d I p. And then this term gives us vi times minus div rho v. Let's keep these notations. I'm going to keep my index notation. dj rho vj. And the index notation is important here because there's a big difference between this vi and this vj. They're doing different things. Okay, there's not a huge difference because it's symmetric. Yeah.
Should there be a minus inside the parentheses?
Yes.
Or out?
Yeah. Thank you. Everything's negative. Let's just factor out a minus sign so that we don't have to think about it. And then we go and collect terms. So I have, let's expand out all the stuff. I've got a lot of parentheses because of how I built the equation. Let's simplify a little bit. I get a rho dj, I got a rho, start over, rho vj dj vi plus 1 over rho, that rho cancels this one, plus dip. Then this v turns into a plus vi dj rho vj. Everybody good here? So this is just simplifying, and then we'll go examine the product rule, and we can see that this thing and this thing combine. And what you do is you integrate by parts here, so that you take these two things and combine them, because I've got A here is rho vj, here this is also A, rho vj, then B is vi here. So this is A dB plus B dA, so that is d by dj, that's my derivative. Now this doesn't work if the derivatives are with respect to different things. So the derivatives have to be with respect to the same thing. So this is d by dxj of A times B, which is rho vi vj. And then this last term, okay, so that's one of the terms that I'm looking for. The other term I'm looking for is P delta ij. And now I have this d by dj, but I also have a d by di of P. So I'm just going to bring this inside. So now I've got di of P plus dj of some tensor tij. Let's not call it tij, we'll call it qij, whatever. So this is the same as dj P times delta ij plus dj qij. So I can slap on this delta ij, which is 0 when I is not equal to j, and 1 when I is equal to j. And then this becomes a derivative over j instead of a derivative over I. Now these are both cycling through all three things, but it's important when I have an equation like this, which index is which. So the j index is getting summed over, but the I index is not. But that's okay, we're just going to move my I index inside. This is a tensor stunt. There's not a lot of tensor stunts like this that I'm going to ask you to do. So then I'm left with this plus P delta ij equals the thing that I'm looking for. Okay, does everybody follow all that? So be very careful when I ask you for a derivation like that you don't do any calculus that you're not allowed to do, which is an easy thing to do calculus that you're not allowed to do, because nothing really yells at you when you do it. Okay, the second one, I think everybody nailed the second one. This is straightforward. I said that rho d by dt of u d squared by dt of u squared plus some constant del 4 of u equals 0. So I gave you this ugly nonlinear, or this ugly higher order wave equation. Maybe it's a wave equation, wave diffusion equation. But now I don't care what this is. It's an equation, it's linear. I can do Fourier analysis on it. And that's the reason why I didn't say anything about what this equation is. I did say I do, but I don't care. This turns into a wave equation. We say u equals u naught e to the I k x minus omega t. So that the second derivative of u brings down 2 times I times minus omega. So this gives us rho times minus I omega squared times u plus c times minus I times k to the 4th times u equals 0. Do a little algebra, expand everything out. This gives us a minus sign. This one gives us a plus sign, right? That's pretty fun. So we get rho omega squared, and a plus sign because I'm squaring, no, a minus sign because I'm squaring I, plus c, I get a minus I square it, I get a minus 1, and I square that, and I get a plus 1. So that's a plus c k to the 4th equals 0. We'll divide by u. So we're left with this dispersion relation. And then we solve it for omega, and omega equals, that goes over there, and I get a c over rho square root of all that times k squared. So my phase speed, dp, is omega over k is c over rho times k, and the group speed is d omega dk, which is, just differentiate this and you get a 2, c over rho k. So do big waves or little waves travel faster in this system?
Big waves.
Yeah. If k is large, the wave is small. Remember, k is inverse wave number. So high k is a short wave. Does that make sense? So when k gets large, v gets large, so shorter waves travel faster than longer waves in this system. Does anybody have any questions about this one? Pretty good so far. Number 3. Number 3 is deceptively easy, and a lot of people went a long way around the horn to get there, but that's okay. C squared is dp d rho. We assume the process is adiabatic, so p equals k, some constant, rho to the gamma. So dp d rho is just the gamma comes down, and I get a gamma k rho to the gamma minus 1. Good? This is just equal to k gamma k rho to the gamma over gamma. Sorry. Rho to the gamma over rho. That's what the minus 1 is doing. And this is just gamma p over rho. Are we good there? And then p equals rho rt, or rho k over mt, equivalent. So we put this over here, and we're left with p over rho equals k over m times t. We'll plug this in here, and we get that. The c sine squared equals k over m times the temperature. Pretty good. So the upshot is, unless you have other effects. So what is this ideal gas law? This is a cartoon model of a gas where you just have hard spheres that bounce off each other. You'll learn that when you take thermo. This is a pretty simple gas. It's a pretty reasonable approximation in most cases. In most cases, the sound speed just goes like the temperature, or the square root of the temperature. Doesn't have to do with anything else. The pressure and the density all only matter as far as the temperature is concerned. Anybody have any questions or things they want to ask about on this one, or went about it in a different manner that they want to discuss? I'm happy to.
I just have a really quick question. Yeah. Don't you have to include a gamma term in the C squared, or no?
Where?
So.
Oh. There?
Yeah.
Yeah, sorry, I dropped it. I forgot it when I got down to this line. Sorry about that. Yeah, because gamma is important. So oxygen has a lower sound, has a higher sound speed than monatomic hydrogen because gamma is larger. Okay. Number 4. Number 4 also saw some curious calculus, but for the most part, everybody got it. So we'll start from continuity, d by dt of rho plus div rho v equals 0. Start with Euler, d by dt of v plus v dot grad v. No, we don't want to start with that. Why don't we start with that? So we're deriving the Rankine Hugoniot conditions, so I'm going to integrate across a jump. I want to write my fluid equations as a full derivative. So the reason I want to use momentum is because it's a conserved quantity, but because it's a conserved quantity, I can write its flux as a full derivative. This one's not a full derivative, so it's hard to. Euler's not a full derivative, so we use momentum, which we just got. D by dt of rho v plus div p delta ij plus rho vi vj equals 0. And the internal energy equation, d by dt of 1/2 rho v squared plus rho e equals minus grad 1/2 rho v times 1/2 v squared plus w
minus k grad t.
Minus the k grad t, but we're skipping the k grad t for now. We'll just assume that the conductivity is infinite or 0. So we'll throw that one out for now. Conducting shocks are other things you can do, but then you've got to incorporate that temperature as well. Everybody good so far? So what are we going to do? So each one of these, and this is actually on the solutions that I put up. This is all I put in the solutions. If you want more details, drop me a line. But the process is the same for all of them. So I got d by dt of q equals minus div f. All of these look like that, where q is either rho or rho v or the total energy, and f is either rho v or this blah or this blah. So we say that this bit goes to 0, so I'm just left with div f equals 0. So then I can integrate from 1 to 2 of div f dx. Now, I guess I kind of glossed past the assumptions that we're making. So, and that's a bad thing to do. We should talk about the assumptions that we're making when we're doing it, but I get carried away because of all the math that's coming. So let's talk about the assumptions. So the assumptions are that first we're in 1D. So x hat is the only direction that matters. And the second is we're in steady state. So that partials with respect to t, I'll go to 0. So nothing's really changing in time. That doesn't mean that the full derivative goes to 0 because the full derivative has a spatial component as well. So we'll just deal with the x component. Vx and x spatial derivatives. So we integrate this, and we're just left with f1 equals f2. Because when I integrate a full derivative across a jump, I get this equals f at 2 minus f at 1, and we know that this equals 0, so f2 equals f1 for all of them. So they all look like this. Do I have another board back here? I do. Donk. That's satisfying. So let's do it for each one of these. The first one I think everybody got. I think everybody got the second one, and people got tripped up on the third one. I'm not sure why I'm holding this. I don't need that anymore. So let's start with the first one. So d by dt of rho equals, let's leave it plus, grad rho v equals 0. So it's just the stuff in the flux. So we're left with rho 1 v1 equals rho 2 v2. So I set this to 0. I integrate this part from one side of the shock to the other side of the shock. I'm left with rho v1 equals rho v2. Does that make sense? I'm going a little quick. I hope that everybody is on board. Holler if you're not. The second one, d by dt of rho v, this is the momentum equation, plus div rho v plus p equals 0. I'm only dealing with one dimension, and we're only going to deal with the x component of things. So the delta is 1. So again, I kill this term, I integrate this term from 1 to 2, and I'm left with rho v squared, rho 1 v1 squared plus p1 equals rho 1 v rho 2 v2 squared plus p2. Are we good? Yeah.
So since it's only in one dimension, that's why it's able to become the v squared?
Yeah.
Okay.
Yeah, that's right. Because we're looking at one dimension, and we're looking at the velocity component along the dimension that we're looking at. So we could do this again and do dt of rho vy plus d by dx of rho vx vy, and then the p term goes away because delta ij is 0. So this is the x direction of the y component of momentum. And we do the same thing. So we set this to 0. This isn't one that I asked you to do. This is just the other component. This also equals 0. So we're left with rho vx1 vy1 equals rho vx2 vy2. Sorry, rho 1 v1x1, rho 2 vx2 vy2. We can simplify this further. This gets real simple, because I know that rho vx1 and rho vx2 are equal, right? So they cancel each other out, and I'm just left with vy1 equals vy2. So if I have a scenario where I've got some interface, so I've got some shock, the velocity into the shock behaves like this. The transverse velocity is just left alone. That's what this says. Vy1 equals vy2. So if we think about the transverse velocity, the shock doesn't care about those. Until you incorporate other effects, the shock really doesn't care about the y velocity. It only cares about the x velocity. Now, such a flow is unstable, as we will show. But, and then the third one we also need that W equals gamma over gamma minus 1 times RT, which is I think you derive this in thermo. I think you need to manipulate the TDS equations to get this, which I think nobody's done right. You'll do that when you do thermo. It's super fun. Well, It's super painful the first time you go through it, and then once you understand it, it's great. Okay, so for the last equation, we're just left with this last bit. So the flux is div rho v of 1/2 v squared plus w equals 0. And then there's a time derivative. We got rid of that guy. So again, we're going to integrate across the shock. Left side equals right side because the integral of d foo is foo. And we're left with rho 1 v1 times 1/2 v1 squared plus w1 equals rho 2 v2 1/2 v2 squared plus w2. And this one we can rewrite RT as p over rho, so w equals gamma over gamma minus 1 p over rho. That's just using ideal gas law. Where did I put it? Oh, it's gone. Anyway, ideal gas law, we used it there. So, and what happens with this v1 and this v2? This trips everybody up too, because this doesn't cancel, or this doesn't like do anything clean and nice, and it's super not there. But these two things cancel each other out because of this one, right? So this guy is equal to this guy, so you cancel you, and this turns into this. So our jump condition for internal energy says that 1/2 v1 squared plus gamma over gamma minus 1 times p over rho, v1 over rho 1 equals 1/2 v2 squared plus gamma over gamma minus 1 p2 over rho 2. Okay. Kind of a gnarly equation, but it doesn't really matter too much. It's just a thing you use when you need it. Okay, does anybody have any questions about this?
I just have one really quick question. What's the argument that allows us to cancel out the time derivative term in every single equation?
Steady state.
Okay.
So we just say that there's a shock, it's propagating. Oh, let me... Bear with me for 4 seconds. And I got... I have...
The ball can only go as fast.
Oh, yeah. Okay, actually. Okay. Let's take a brief detour and watch some movies. Remember watching movies when you were a kid in class instead of actually doing stuff? Every now and again, my kids come home and they're like, we watched Fantasia in band. It's awesome. I never watched it. Oh, did you really? Was it good? So here, this is like 2 minutes long. This is a holdover from last week.
This thing faster. And I started thinking about how a supersonic wind tunnel works. And so treated this like a supersonic. And so treated this like a... The ball can only go as fast as the air goes. So it came down to a problem. How do I make the air go through this thing faster? And I started thinking about how a supersonic wind tunnel works. And so treated this like a supersonic wind tunnel.
This is completely off topic.
You put the vacuum pump up to it and you draw all the air out until you've got essentially a full vacuum in here. The air all rushes in, pushes the ball down the tube. Well, ping pong balls don't go very fast because of wind resistance, drag going through the air. Well, there's no air in there. The idea was to put a seal there and then add two pieces. One is a nozzle, call this converging diverging nozzle. This is what you see on rocket engines and supersonic wind tunnels, things like that. Put a seal there and then put a pressure chamber back here. So there's pressure here. So the air here is denser than atmospheric, and it's a couple of atmospheres. There's still a vacuum in here, and the ball goes there. So what happens now is when this seal breaks, we just pump this up until the seal breaks. Air rushes through here, but when it goes through this nozzle, it comes out through the other end of the nozzle going supersonic.
that Barry Manilow?
Yeah.
Is there any more actual science in this?
There is no money that could get me to stand in front of this thing.
So anyway, Purdue University, get your engineering degree and go break stuff. I know. Okay, this is the thing that I actually was pulling up. That just happened to be in that directory, and I meant to pull it up a while ago.
Ping pong ball finally got its revenge on the cat.
That's right. So this is just a ballistic that gets launched supersonically, and here, this is pretty great. You can see the shrapnel from the casing that it lived in is all traveling all along with the projectile. But we're going to get to this. They've got these boards that have lines on them. So this thing is traveling, and does it say up here how fast it's going? It's Mach 1.5.
I guess it
think.
shows how many seconds it has.
Yeah, so we can calculate how fast it's going in a second when it gets to the barrier where you can actually see the bow shock.
You've already passed one board.
I know there's another one coming, I'm pretty sure. Oh, that's boring. Let's go back to... There we go. There you go. You see the shock? Oh, I should put this on that. So here is a shock. You'll notice that it's curved. Oh man, can I do that angle off the top of my head? It's fascinating. I know this derivation, but can I do it in front of people? So I'll do a shorty version of this. When you have something that's traveling faster than the speed of sound, it makes a shock wave. And if I have a projectile, now I'm an astronomer, so let's pretend that this isn't a ballistic to hurt people, but a space capsule is coming back into re-entry from doing science on outer space. You get a shock that travels like that. And the shock is traveling in this direction at the Mach number, which is some fraction of the speed of sound, and in this direction at the speed of sound. So now I forget which angle you actually measure. So anyway, you can sort out based on the angle. I'm going to abandon ship and not do any more math because I'm going to screw it up. Yeah. Oh, yeah. So you got a shock like this. The opening angle here is set by the sound speed and the Mach number. So from the opening angle, you can get that. You can get the Mach number, and it should go, if you draw the right picture, the Mach number goes like 1 over the sine of the angle here. Now from that I could probably sort it out, but I'm standing in front of people and you don't want to solve problems for 2 minutes. So the Mach number is 1 over the sine of the opening angle. So this is what one of these shocks looks like in real life. So all of this stuff with Rankine and Hugoniot that we've been doing is about this part of the shock. This part of the shock, you have to think about it going in that direction. This part of the shock is traveling in x, and the only velocity component you really care about is the velocity component in x. And so from the opening angle, you can see how fast it's going. So for a shallower opening angle, it's traveling slower. And you can see that this one is traveling at a Mach number of a couple. Let's see. There was another shockwave picture that oh. I think this is the graphic that they used. This is my pictures. This is my pictures directory that of things that I was supposed to pull up in class, but I never had the laptop open. What does this tell us? This tells us how big the explosion was from the Trinity site. So this, I'm like 80% sure. I've lost the provenance of this image, but I think that this is the image that was published on the New York Times. That gives away. This gives away classified nuclear secrets. This picture does. How do you see that this is classified nuclear secrets? Because we know how this blast wave evolves in time, and we have the time, so we can get the energy, because that's the only other pre-parameter. Anyway, I'm trying to think if there's something else that I needed to say about that image. Anything else cool in this directory? This is the Trinity test. So this is the explosion front from the first atomic bomb, which looks weirdly like a jellyfish. Oh, maybe actually this was the image that they used. This is an easier image to use because this tells you the radius of the explosion with time. Okay, anyway. Right. Miscellaneous things. Okay. Does anybody have any other questions about the Rankine-Hugoniot solutions? So the basic idea is the Rankine-Hugoniot solutions tell you what happens across a shock. I don't need that. I'll break everything. Okay. So Berger's equation. So this last one was method of characteristics. I do hate this board. Okay. So this last one is on method of characteristics. And more than one of you said, this problem took me like an hour and a half, but it should have only taken me 5 minutes. And that's okay. That's fine, because it's not actually all that complicated once you see how to do it, but it's kind of complicated until you see how to do it. A lot of things are like that in life. So, the equation that we start with is Berger's equation, which is du dt plus u du dx equals 0. Now, this is like Navier-Stokes and Euler, which have stuff on the right-hand side. Here, we're just looking at the left-hand side, just the left-hand side. So, what I say is to show that if I start with u of x and t equals 0 equals minus mx plus b, so that means as x increases, the velocity goes down. That means you're going faster than the dude in front of you, slower than the dude behind you. Then show that this implies that u of x and t equals b minus mx over 1 minus mt. So show how this works. So from this equation, I have full derivative du, full derivative dt equals 0. That is what this equation says. For this to be true, I also need dx dt to equal u. Are we good with that? This is necessary for this u to show up here. So I can integrate both of these things. All I've done is taken this equation, which has 2 terms in it, and turned it into 2 full derivative terms. And now these tell you what you learned from freshman calculus. This says du dt is 0. That means that u is a constant. That means that u equals constant. We put a little bit more meat on what u equals constant means. This means that u of x and t equals u of x naught t naught. That's what u equals constant means. And this one I can integrate. I mean, I can integrate with this with respect to time. I know that u is constant with respect to time. So when I integrate it, I integrate both sides with respect to time. I integrate the left-hand side, and I'm just left with x. And the right-hand side, I'm left with ut plus x naught. So now for every point x naught, I have, we'll just reiterate, x naught equals x minus ut. And then we plug in. So now I'm done for the most part. I just got to do a little bit of algebra, but I've set up all the heavy machinery. So I take this, and I take my initial conditions, and I'm left with u of x and t equals minus m x minus ut plus b. Because x naught is just this. And then I solve for u, and u equals, you got to do a little bit of algebra, and I'm just going to assume that I did it right before, minus b minus mx over 1 minus mt, and you can see that this blows up when t equals 1 over m. Yeah.
So we said that that du dt is 0 from Berger's equation, but we had to assume that dx dt was u. So how can we say that dx dt is u? How do we justify that?
Because of chain rule. So these two things are true together. So if this is necessary to be true for this to be true, and when I chain rule this out, when I chain rule this, I get du dt equals partial u partial t plus partial x partial t partial u partial x. So this is just chain rule, and then this equals u is this other equation. That gets me up to here. So I get this equation just from chain rule. Du dt is partial u partial t plus partial x partial t partial u partial x. Blah. So here's chain rule, which looks just like my other equation, except I've swapped this bit with u.
Is that supposed to be a partial derivative?
I can keep this one a full derivative because x only depends on time.
Okay.
Cool. Any other questions on this one? It's a little weird, I'll admit. But the reason that I like it is it shows that this part of Navier-Stokes is real unstable. That you can set up this problem such that it blows up and you get infinite velocity in a short amount of time. Now, and I've said this before and I'll say it again, I add on 1 over rho grad p, my sign, plus nu del squared v. I know that this isn't much, this is just pushing, that's okay. It doesn't really change anything. You can show that Euler's has a finite time singularity too, I'm pretty sure. But once you introduce this del squared v, I'll talk about diffusion. This is really well behaved. This smooths everything out. This is super not going to explode. Diffusion doesn't explode. So when I combine these two things, then I get something that if you solve it, if you can actually say something, you'll win the Nobel Prize. I'm pretty sure of that. If you can actually solve the solution space of Navier-Stokes. Okay. Then the last one, which I think everybody did pretty good on. Deriving sound waves. I'm just going to go through it to give you guys an opportunity to holler for things that you want to talk about, or things that you think you did differently than I'm doing it, and you want to see if you did it right, or because there's more than one way to do these kinds of problems. And how did I say it? And I spelled it out to make sure that you got all the things, but this is the kind of thing that might show up on the final for the midterm, because I think it collects a lot of good ideas. And I think you can do it really fast. Or you should be able to. I haven't written the midterm yet, so don't get too scared yet. So start with d by dt plus rho plus div rho v equals 0, and d by dt of v plus v dot grad v equals minus 1 over rho grad p. These are our friends, continuity and Euler. So the first thing we do is we start off with rho naught is a constant, p naught is a constant, and v naught equals 0. And I would encourage you to stick with the v naught equals 0 form of this derivation rather than trying to use some non-zero v naught and then have to do Galilean boost, because that's really, if you started this problem with v naught is some constant that's not 0, you would then boost to a frame where it is 0. So this is actually a general solution, because I can always change velocity. I can always just subtract a velocity, unless we're going too close to the speed of light, and then you got to do a different transformation, but this is non-relativistic. Supersonic, not relativistic. So we start with this constant equations, and we see that these solve this equation because the derivatives of constants are 0. So then the next thing we do is linearize both of these. So we say that rho equals rho naught plus rho 1. You could also say rho naught plus delta rho, which also works great. And v equals, we're just going to call this v1. And I guess we got to linearize p equals, well, we just get rid of it. Let's just get rid of it right now. Minus c squared over rho grad rho. What assumption do I need to make this transformation?
It's adiabatic.
It's got to be adiabatic, because otherwise I get another temperature term, or however else you do the rest of the chain rule. So this is an application of chain rule where there's only one term, whereas this application of chain rule, there's a bunch of terms. Okay, into here. d by dt of rho naught plus rho 1 plus div rho naught plus rho 1 times v1. You could have two terms, but we'll get rid of them. This guy is 0. Let's expand this one out. This becomes div rho naught v1 plus div rho 1 v1, and we throw out this term because it's second order, and that's how we're playing this game. This game is the throw out second order terms game. Equals 0, and we're left with d by dt of rho 1 plus div rho naught v1 equals 0. So the important thing that I'm looking for here is that this is rho naught and this is the perturbed v1, and we only have one v1 term there. Then for the second term, we're left with d by dt of v1 plus, that's a v1 and that's a v1 and that's two v1s, and the whole thing goes away, plus nothing, equals minus 1 over rho naught plus rho 1 grad, c squared, grad rho naught plus rho 1. This one is kind of ugly, but it's not too bad. We just got to do a Taylor series on this. That Taylor series looks like minus c squared 1 over rho naught times 1 minus rho 1 over rho naught squared. This is times grad rho 1, because grad rho naught 0. That term goes away. And then this term goes away again because I've got a rho 1 or rho 1, that one's squared. So the right-hand side, you're just left with minus c squared times 1 over rho naught grad rho 1. So the linearized equation is d by dt of v1 equals blah times grad rho 1. Okay, let's write these up here. dt of rho 1 equals minus dx, here I'll switch to x, then erase u, of rho naught v1, and rho naught dt v1 equals minus c squared dx rho 1. Did I do that right? next, then I cross differentiate and I add them together. I can do that slow if you want, but I'm just going to write down the answer. D by dt of rho 1 minus c sound squared dx rho 1 equals 0. And then I drop in rho equals rho naught e to the I k x minus omega t. This is like Zeno's chalk. It's like every second is half the chalk it was before. And then we're left with omega squared minus c sound squared k squared equals 0. And our phase speed Vp is omega over k is c sound. Yeah, I did the last chunk really quick, but I think I've done it a couple of times, and I think you've all done it on homework. And I think everybody seemed to get it. Is anything that, no shame, of course, is anything that anybody wants to talk about or go through slower? Yeah.
So the CS is just the C from the previous equation.
Yeah, that's right. Yeah, this shows up right here when we get rid of pressure. So, C sound you should really think about as the contribution from pressure. Okay. All right, now, does anybody have any questions about any of those homework problems? I like all of those problems, and as far as midterm prep goes, you can expect to see basically any of those on it. I'll go through and make sure that it actually fits into an hour. This is why I ask everybody how long it takes you, because if everybody says that problem 6 took them 4 hours, then I probably won't do that. But I don't think it did. Okay, so now I'm going to go back and talk about these interface instabilities again. So now I'm actually going to make this another video. If I do this, then I know what the video is about without